Welcome to the Ergonomics seminar. Today we're going to explore how ergonomics is important in the workplace and some of the elements that are particularly important related to not only tooling, but also the positioning and the way our operators work. You can see in front of you an agenda. We're not going to go through each of these bullet points individually, but it's just important to note that we're going to start with a high-level bird's eye view of things, and then we're going to dive more into each individual element related to ergonomics as we move forward. So to begin, we're going to look at the basics in tightening technique. This will be a very brief section before we dive further in. And the first thing we want to look at is why tightening? Why do we even want to use tightening? Why is tightening important? So from a general sense, we know that there are a lot of different ways to connect parts. We can do it through gluing, welding, soldering. Any of these, facets of connecting parts are important and useful in their different ways. But the most common way to connect parts is, of course, through tightening. Hence, we're going to focus on tightening as we move forward through this presentation. But the question on everyone's mind then is, if tightening is the most common way to connect parts, why is it the most common way? And primarily because there are a lot of really good advantages related to tightening. First off, it's very safe, which is very important. Safety is always key. Also, it's fast and easy to disassemble. So let's assume that we had something go wrong in production and we need to remove and reconnect parts. If we did the connection through tightening, it's very easy to take off the parts that were bad or assembled wrong and reassemble new parts. And also, it's easy to produce, which is very, very important when we have numbers to hit and things of that nature. Related to tightening though, there is some considerations we want to have. First off is torque spread. Torque spread is the most amount of torque used to overcome friction. So this is something we want to keep in the back of our minds. In addition to the effects of lubrication on tightening. When we consider the effects of lubrication, first off, the friction coefficient will be reduced if we use lubrication for our tightening. Also, more torque will be transformed into clamping force. And there is a risk of unplanned damages if we possibly over-lubricate parts during or prior to the tightening. Now, though, we would like to move into the basics in power tool ergonomics. But before we do that, let's have one specific definition we want to look at, and that is clearly the definition for ergonomics itself. So we're going to start with a coin term, work smarter, not harder. This is something we've all heard at least once in our lives. It's very much applies to everything we would do, I would say, especially when we're looking at production and producing parts. And what does that mean for us when we look at the definition of ergonomics? So ergonomics is the scientific study of people and their working conditions, especially done in order to improve effectiveness. And this definition was pulled straight from the Cambridge Dictionary for reference. And what that means for us, to simplify things, is that the objective is to optimize performance and human well-being. So to start off here, let's look at a video. This video is going to be a bad example of ergonomics in excavator assembly specifically. So let's play this video and talk through it. So looking at this video, there's a couple things that stand out as obvious indicators of poor ergonomics. First off is the way and the position the person is sitting in. So this is not an ideal position to be sitting in using, especially a tool of that torque capacity holding over your head. You'll see the gentleman tries to get some leverage off of the actual application itself with his feet here to try to make the most of what he has. But considering body position and the tool he's using, this really is not a great position to be operating in. We can only imagine if we continued to operate in a position like that eventually we would have some sort of injury, right? Which leads us right into workstation ergonomics related to absence rate in the workplace. So we can state that the absence rate increases due to poor ergonomics. So we have a 20% higher downtime costs due to high amounts of ergonomic loads. Also, we can see that there's a 40% higher rework cost due to high amounts of ergonomic loads. So not only are our employees off work, so to speak, longer due to poor ergonomics, also the quality of the work they're doing is a lot poorer with poor ergonomics. This is something that's going to be very crucial for us to remember moving forward. So when we look at demographics as a very, very important element of ergonomics, we can see two very specific facts. One is the average age of employees is increasing in the workplace. So in the year 2020, 46 years old is the average age of the employee in the workplace. And in the same year, 45% of employees are older than the age of 50. So as we all know, as we age and get older, we don't have the same capabilities that we might have had as a younger person, generally speaking. And these are things we want to consider as we look at the tooling and the things our operators are working in and the positions and environments they are working in. Now let's look at the influencing factors. We have three different elements, we're going to call them here. The first is our workstation. These are things like, are we standing, are we sitting, how well lit is the area, what kind of noise are we experiencing. The next will be the operator specifically, so their gender, their age, right, the demographics we just touched on, maybe their arm length, so different things that vary from person to person. And lastly, the one we want to focus on is power tool ergonomics. So the weight and the balance of the tool, the handle design, how easy it is to use, etc. And on this chart in front of you, we're going to focus on external loads and vibrations of these different components specifically. So let's start with external loads. Here we have another video we're going to play. So this is going to be a bad example with a right angle electric nut runner. So when we watch the video, we can see that though it might be a quite silly video, it's actually quite dangerous. So what happened in this video? Why was the gentleman twirled around like that by the tool? Well, we can relate that incident specifically to inertia. So what is inertia? Inertia is the resistance of an object to change its state of motion. We might all remember this definition from science classes we had historically through school, but let's kind of make this relate more to what we're talking about now, and let's look at inertia in tightening, which is the torque reaction due to the bolt's resistance to rotate. So in the video we saw previously, the tool was rotating him around the bolt because the bolt did not want to rotate. So its resistance overtook the tool's strength, if you will, and it twirled the gentleman around, which is actually quite dangerous. Also, reaction forces is something very important we need to remember. So we can see in front of us here a brief description that an operator is not able to react on an event that happens in less than 300 milliseconds. So nobody's Spider-Man, nobody has instantaneous reactions. So this is something we need to be aware of. So now let's combine inertia and reaction forces, those two previous elements together, and let's look at inertia and energy used. So for this, we have an example of a boxing bag, and as you can see in front of you, it's red because what happens? We can make the assumption that in this image, the person is punching their boxing bag quickly and aggressively. So what happens? They're reacting very, very quickly, but they're not getting much reaction or results from that, but they're also burning a lot of energy. As opposed to, in the next example, they're not reacting as quickly necessarily, however, they're exerting a lot less energy and they're getting better results and they're moving the bag a lot further than as if they were to exert a ton of energy and work extremely rapidly. So what does that mean for us? Always trying to work faster and more aggressive doesn't necessarily pay off, and it does burn more energy. Two other things we need to keep in mind are that a shorter tightening time of less than 40 milliseconds does equal a large reduction of reaction force, and a long tightening time has a small reduction of reaction forces. So if we want to consider this idea, if we go back to the boxing bag example, the quick punches would mean that once they were done punching, the boxing bag, as you could imagine, didn't move very far, so its return to sender essentially would not be very much, whereas the person that pushed the boxing bag very far, if they were to let go of the boxing bag would come swinging back, so a larger reaction. That's the one additional component we have to consider. Furthermore, we do all have limits. We're all human. Some of these limits we want to look at first off is muscle strength. So everybody has different capabilities when it comes to their own physical strength. Also, the force buildup does take time in muscles, so it's not instantaneous. And this correlates directly to our own personal reaction times. So this is a general statement, but we've found that essentially 120 milliseconds is the time for our body's natural reflexes to react, and 300 milliseconds is the time you can consciously react. So let's relate this back to the video of the person that got turned around by the tool. So they were not able to consciously react because that tool jerked them so rapidly fast that they were already spinning around before they realized what was happening. And if we don't adhere to these limits, there are some painful consequences, right? We've seen them in the videos. Also, we want to keep them in mind. For example, here, busting his knuckles on the side pipe. Maybe rotating around, twisting our wrists, things of that nature. So if we don't adhere to our limits, there are some consequences that occur. That's why we want to remember these and keep them in mind for operator safety. So that's great and all, and it's important to remember, but how do we really manage torque reaction? That's the big question on everyone's mind now. Is, okay, we see the challenges, but how do we manage those challenges? So starting off here, we do have a little chart that gives some examples of torque reaction and when you should use some kind of torque reaction device. So let's look at the chart. We can start off with maybe an air tool. So if you're using a pistol grip air tool, anything that's greater than or equal to 6 Newton meters, it's good to use some kind of reaction device. If we look at an EC tool, for example, an angled EC tool, anything that's greater than or equal to 50 Newton meters is when we recommend you use some kind of reaction device. So what are the options? First off is a low reaction tool. Low reaction tooling is something that's becoming more prevalent in the industry as we move forward in time. So this gives the operator almost the feeling of no reaction, essentially. Also, torque arms have been around for a while. These are options we can use to manage torque reaction, in addition to reaction bars. Reaction bars are also have been very prevalent for years and are a great way to manage that reaction. That way, in instances where we are running into maybe operations that are less than 300 milliseconds, for example, and we can't react, the reaction bar will dull that reaction down for us. Furthermore, vibrations is a super critical element of ergonomics that we have to look at. And to start this section off, when we look at vibrations, we have to remember one thing on the top of our mind: it's not always about the tool. So in this video, yes, the tool probably is relaying a lot of vibration to the operator. However, it's also, if we look at the socket, that is also providing terrible vibration feedback to the operator. In this case specifically, they should be using ideally a guided socket, which they are not. Now that we know it's not always about the tool, so we don't want to take for granted by saying it's not always about the tool to mean it's never about the tool. So here we have a video that's going to show the differences that tooling can have relating to vibrations for our operators. So here we can see a dampened riveting hammer, and we can see on the arm of the person it was not reacting much, versus a conventional riveting hammer we see here, which is almost violently shaking the person's arm, which is very, very, very poor relating to ergonomics. That is not a good position for someone to be operating in for any amount of time during any day. And what happens if we continued operating? What happens if we continued using that non-dampened or conventional tool throughout the course of every day for 5 days a week, as an example? Well, more than likely we'd develop some kind of hand-arm vibration injury. So what would happen if we continued to use a conventional riveting hammer or some kind of non-dampened tool maybe 5 days a week for the course of our work history or our work career? Most likely we would develop some sort of hand-arm vibration injury. The sad news is that these actually are all permanent and irreversible. So these are not something that we can just take some medicine and fix and make go away, unfortunately. Some examples of these would be like a vascular disorder, a nerve injury, or a muscle and joint disorder. And we'll give an example of each of these actually now moving forward. So we look at vascular disorders. An example of this would be white finger syndrome. This is something maybe we're familiar with or have seen before. It's quite unpleasant. It does lead to a reduced sensibility in the fingers. You have no bleeding during the episode. And obviously the most important thing, and why it's called this, is the appearance of white fingers, as seen in the image on screen. Moving forth, nerve injuries are also something we could develop. This would be something like a sensation of pins and needles, a loss of grip, or carpal tunnel syndrome. When we think of pins and needles, you could only imagine We've all had our hand fall asleep at some point, I'm assuming, in our lives. So imagine if that was a continual thing that you experienced very often, not once in a while, maybe if we sat on our hand too long or something. Also, musculoskeletal disorders are another type of hand-arm vibration injury. A really good example of this display would be osteoarthritis, which is also known as joint degeneration. If anybody is familiar with arthritis, we know that this is not something that you just wake up one morning and you magically have arthritis. This is something that is developed over the course of time as we age. Using a non-dampened tool would increase the chance of us developing something like osteoarthritis or any of these other hand-arm injuries that we reviewed over the last few slides. So these injuries do take years to develop. So relating to this specifically, we have two charts on the screen in front of you, starting left to right. So if we look at the first chart in blue, so this is an example of car mechanics using impact wrenches. This chart and information is dated intentionally. We have a reason for using older information here. So if we look on our X and Y axes, we can see that on one hand we have the percentage of vibration white finger cases, and on the other hand we have the years of exposure to hand-arm vibration. We can see that the percent of vibration white finger related injuries increased as the years of exposure to hand-arm vibrations also increased, which we would expect. However, the good news is if we move to the right-hand chart, which is in red, from the years of 2008 to 2017, more recent information, we can see that the hand-arm vibration syndrome cases and carpal tunnel syndrome cases have decreased. There's actually a general reduction in the number of new claims. And this is really great news. This means that companies are taking ergonomics seriously, and they know it to be as important as it is, and they're looking at implementing not only tools that help reduce these injuries, but also looking at implementing shift changes and things of that nature to help reduce the exposure operators have. So what kind of solutions do we have to vibrations, right? We just mentioned two of them, tooling and shift changes. So first off, you can see here not only tooling, but also something like a guided socket is very important to reduce vibration on the operator. We saw a non-guided socket in that first video in the vibration section, and we saw the kind of impact that could have on not using the proper socket. Now let's move on to body and wrist positioning. If you look at the sketch in front of you, you can see the woman is in a very poor position. She's hunched over with her shoulder arched up and her wrist is bent using a pistol grip tool. So this is not an ideal situation for someone to be working in. Why? Because it can lead to injuries like carpal tunnel. So we always want to make sure we're working in a straight wrist position to avoid any bruises on our tendons and nerves. So doing something like that for 10 minutes once a year is not a very big deal, but we have to consider operators who are using these tools day in and day out. If someone is to work like that in that position, that would be very, very negatively impactful on their body. And they'd have a higher chance of developing something similar to carpal tunnel, if not carpal tunnel. Furthermore, the University of Windsor actually did a study based on the specific types of tools that are in our production floors and environments, and the way you should be operating and positioning yourself using those tools. So if we look at this diagram here, specifically there are 4 different ways we could be using this tool. However, only one of those is an ideal way. In this example, location 4 is the ideal way for us to use this specific type of right angle tool. We should be standing up straight with the tool directly in front of us at chest level, facing down on the application. Something like location 2 is extremely unideal, hunched over with our arms extended and the tool stretched away from us. There are different positions for different tools that we want to keep into consideration. This is only for right angle tools. Obviously something like a pistol grip we've covered, you want to have your wrist straight and your arm not extended, as an example. So we've covered some pretty impactful considerations relating to ergonomics. So external loads, vibrations, our body and wrist positioning, which we just covered most recently. The big thing to remember though is how we manage those. So we have a lot of solutions available to us today in the forms of tools and how our operators work. So we have low reaction tooling, we have guided sockets, we have things like reaction bars and torque arms. So there's a lot of things available to us to make sure that we are giving our operators the most ergonomic solutions possible as they work. In addition to the more human elements, like making sure we change shifts and don't have people working on one tool or one application that could be not as ergonomic too long. In summary, ergonomics does improve productivity, and it also improves overall quality, which leads to a direct correlation of a decrease in costs, which is a win-win for everybody from operators to businesses alike. That concludes our ergonomics seminar. Thank you for watching.